Welcome to this year's Sutherland lecture on New York skyscrapers, origins and technology transfer.
Well, thank you, Andrew. Despite the title, skyscrapers are sort of incidental to the research that I've done. I've been working as a structural engineer since 1987, and about 3 years into that career, I started doing research on old buildings, not because I thought I would end up here someday, not because I thought I would be talking about it or publishing about it, but because as a designer, as a very low-level designer, I needed to understand the buildings that I was working on, which didn't look anything like the things in my textbooks. I had been taught, as all structural engineers are, how to design a new building. I had not been taught how to understand old buildings that don't look like the new buildings. So I started doing research, and what gradually came out of this was a view of the history of this, that there was a huge change in building technology in the United States between 1870 and 1900 or so. Similar changes were taking place in other countries. Everybody was heading in roughly the same direction. The US has, as I'll be talking about today, sort of some peculiarities to that history. And I think those peculiarities are related to why we developed skyscrapers with that new technology and other people did not. Certainly the new technology was in use everywhere in the United States, and similar versions of technology were in use in the UK, in France, in Germany, and so on. There's sort of a peculiarity if you look at skyscrapers as a technological object, which is new technology tends to be used first in small versions. With the design of large steel frame buildings, the large is actually an important word. There was no point to building a small steel frame building in 1900. You could just as easily continue to use the old technology and use brick bearing walls. So you have this inversion of the normal procedures, the normal path of technological change, where the early versions were much bigger than everything around them. And I'm going to start with really the simplest question is, what is a skyscraper? We have, in 2024, we have certain opinions on this topic, but put yourself in the mindset of somebody in 1900. What's a skyscraper? And if your answer is that it is a very high up sail on a fully rigged ship, you are technically correct, but that answer is useless for this conversation. So there is no generally accepted, even today, definition of the word skyscraper. It's a tall building. But what's tall? What's a building? Most people end up with a definition that is somewhat similar, and this is a cultural reference that I'm going to explain because most of you are not going to know it. In 1964, the United States Supreme Court was looking at a question about obscene materials. And Potter Stewart, who was one of the justices, said that he couldn't provide a definition of obscenity, but he knew it when he saw it. That is where we are with skyscrapers. People look at a building and they say it's a skyscraper or it is not, and you have to try and decide. So I'm going to begin with several negatives. The building on the far left is the World building in New York, the World newspaper. The building second from the left is the Monadnock building in Chicago. Building third from the left is the Rookery in Chicago. Monadnock and Rookery are both internationally famous as early skyscrapers. The World building is not as famous. It was the tallest skyscraper in the world for 2 years, 1890 to 1892. So while you don't know it, it is a building to be reckoned with. None of those three buildings, well, the Rookery and Monadnock are both still there. The World was demolished in the 1950s. None of those buildings has a skeleton frame. So skeleton framing is obviously not necessary unless you want to argue that the Rookery and Monadnock are not early skyscrapers. You're welcome to do so. People in Chicago will disagree with you. I should also point out that skeleton framing, unlike skyscraper, has a definition. And it's actually a definition that's very amenable to structural engineers. It's based on load. A skeleton frame building is one where the building frame carries all of the loads, carries gravity loads, carries lateral loads. That's a very clear-cut thing, and it's pretty easy to look at a building most of the time and decide, does it have a skeleton frame or not? The thing on the far right is not a chimney. It's in New York. It was in New York. It is the Colwell Company shot tower. For those of you unfamiliar with shot towers, you dump molten lead at the top, and as the lead falls, air gradually turns it into a series of little spheres, and you go to the bottom and you collect the shot that you can now sell. You can see in this picture, the building had a frame, or the shot tower had a frame, consisting of cast iron columns and wrought iron beams. I would argue it's not, by the definition I just used, a skeleton frame because the frame was incapable of carrying lateral load. The masonry infill, the walls, were shear walls rather than being curtain walls. However, the people who built it thought the frame was carrying the lateral load. They thought the frame was competent to do so. And in the spirit of generosity, I'm going to say that this was sort of an early skeleton frame. I'm pretty sure no one thinks it's a skyscraper. So skeleton framing is not the answer. On the left, we have the tallest structure in the world, tallest structure in the world, the Great Pyramid. Tallest structure for, 3,800 years or something, which is a record that's unlikely to lose. Most people would not argue it's a skyscraper. There is at least one architectural historian who believes the pyramids were the predecessors to skyscrapers, so I have to say most. I would argue it's not even a building. It's a human-made structure. I like to think of a building as having usable space inside. On the right, we have Ulm Minster, tallest human-made structure in the world from 1890 to 1894, actually overlapping with the World Building, except that the World Building was occupied at every level. World Building was 25 stories tall. Ulm Minster, for all of its height, is effectively a two-story building. So again, if you want to argue that's a skyscraper, I won't say you're wrong, I'll just say I disagree with you. Maybe it's height and slenderness. On the left, and this is a picture I chose deliberately. On the left, we have Trinity Church at Broadway and Wall Street in New York, overshadowed by 71 Broadway, the building on the far left, which was a very nondescript office building that's been converted to apartments. Trinity was the tallest structure in New York from 1848 until 1890 when the World Building was built. Tourists used to go up that spire. I'm not sure why. I've worked on restoring that building, and the view from the windows in the spire is terrible. Their windows are this big. But people would go up that very tight spiral stair to look out those windows because it was the tallest structure in the city. So maybe not such a great example. Everyone knows the structure on the right. I would argue that's even less of a building than the Colwell Shot Tower. It's a fantastic structure. You will not hear me criticize the Eiffel Tower's engineering, but it's not a building to me. And again, if you want to argue that it is, I'm not going to say you're wrong, just that I disagree with you. Is it metal framing? And this is where things start to get a little bit interesting because I'm now talking about something other than geometry. Some form of modern technology sort of seems to be required for a skyscraper. This is the Howitt Building on Broadway in New York, constructed in the 1850s. And on the picture, on the photograph on the left, everything you are looking at except for the fire escape and the windows is cast iron. 100% of that facade is cast iron except for the things that obviously are not. Is this a predecessor to modern technology, modern framing? And the answer is not really. That is a bearing wall. And the connections between the pieces of iron, and I've actually analyzed this for a similar building. I have not analyzed it for Howitt, but I have seen the details of the connections there. the connections are not capable of carrying enough moment to make this a moment frame. It looks, if you look at the elevation, looks like maybe it could be a moment frame, but it's not because the connections are inadequate. It is a bearing wall. If you simply replaced all those pieces of iron with identically shaped pieces of masonry, you would not change the structural action at all. So this is proof that you can have a metal frame structure that really is not modern in any meaningful way. It's a beautiful building, but it's just not, given its height, it's not a skyscraper, but it's not even a step towards being a skyscraper. I feel like I've done enough negativity for a bit. If I'm going to do this, I have to tell you what I think. The first thing is it has to be a usable building. And I know several architectural historians who argue it has to be a commercial building. In other words, you can have a skyscraper that's built for non-commercial purpose. There certainly are some in New York. The Rockefellers built a church where the thing that looks like a church tower is actually pretty much a 20-story skyscraper, but that's the Rockefellers being the Rockefellers. So you have to have space on the inside that is used in an ordinary manner for a building, and there has to be some kind of proportionality between the height of the building and the amount of space. If you double the height of the building, well, you have setbacks. Maybe you don't double the space, but you significantly increase it. And that rules out the pyramid and the churches and the Eiffel Tower and so on. It has to be tall for its context. If you build a 10-story building today, nobody is going to call it a skyscraper. Certainly in New York, a 10-story building barely makes it to be called a mid-rise. If you built a 10-story building anywhere in the world in 1890, it's a skyscraper. Or at least it's the height of a skyscraper. So the context matters. If any of you are familiar with the musical Oklahoma, there is a song that contains a line. There's a song, Everything's Up to Date in Kansas City, that contains a line, they went and built a skyscraper 7 stories high. That song, the events of the musical are taking place in 1907. And the problem is that song is historically inaccurate because in 1890 there was a 10-story building in Kansas City. Interestingly enough, built by the New York Life Insurance Company. New York Life Insurance Company built a series of local headquarters buildings across the Midwest of the United States. And every one of those buildings was either the tallest building in the city where it was located or one of the top 4 tallest buildings. There are, I think, 5 of them. And if that is not architectural imperialism, building a skyscraper to say that the New Yorkers are here, I don't know what is. So tall for its context. And finally, back to the issue of metal framing, there should be some level of, let's call it industrialized technology, things that couldn't be done in the UK before the mid-18th century and in the US before the mid-19th century. Cast iron, chronologically, really came first as a building material in the United States, followed shortly afterwards by wrought iron. We didn't start producing steel on an industrial scale until the 1870s. So then you get steel. For a long time, people would use both wrought iron and steel sometimes in the same building based on which one was cheaper this week. Reinforced concrete comes later. Something I can say pretty much everyone agrees on. We know the first reinforced concrete skyscraper. It's the Ingalls building in Cincinnati, built in 1903. It's 14 or 15 stories tall. The previous reinforced concrete buildings had all been 3, 4, 5 stories. So Ingalls stands out, but that's 1903. There were plenty of skyscrapers already built by then. Now we get to the engineering portion of the lecture, which I promise I'll try to get through quickly. In order to understand the way the technology evolved, you have to have some way of categorizing it. It is extremely easy to find an architectural history that says people were building bearing wall buildings and then they started building skeleton frame buildings. And the problem with that is describing a race as 50 people started running and 1 person finished first. It doesn't really give you the picture of what happened. So you have to understand what happened in that 30-year period I mentioned. And to do that, you need some way of distinguishing one structural type from another. So being a structural engineer, I'm using load as my distinguishing characteristic. What supports the gravity, and I'm not going to keep saying floors and roof. If I say floors, I'm including the roof. What supports the gravity load of the floors, the dead weight of the floor, the occupancy load on the floor? There are basically two options. It can be supported by masonry. It can be walls or piers. I don't care. I'm using walls to keep the amount of text on the slide down. Or is it supported by metal framing? If we're talking about the late 19th century, it's not going to be reinforced concrete. It would have to be metal. So what supports the gravity load of the exterior walls? Again, one of the characteristics of a skeleton frame building is that the frame supports the exterior walls. What supports the building when there's wind? In the 19th century, people weren't designing, or not designing they were not designing in the modern engineering sense, which is to say analytic design for seismic forces. They knew in some places that they had to worry about seismic forces, but they didn't have a form of analysis that really worked on it. So what is supporting the building when the wind blows? Why doesn't it fall over? Three loads. If the answer to all three of those questions is walls, it's a bearing wall building. This is traditional construction. If the answer to all three of those questions is framing, it's a skeleton frame building. That's the end of the race. And again, structural engineers are the ones who define skeleton framing in this manner. If you have the walls supporting themselves and the floors are supported by metal framing, there are two versions of that. You're in the middle stage of development. You're seeing the horse race right there. And at the time, in the late 19th century, early 20th century, these buildings were often called cage frame buildings. There are also people who decided to confuse me, not knowing I was going to be born 70 years later, and flipped the words skeleton and cage from the way I've defined them here. But ignoring that, we still use the word skeleton framing to describe that particular type of building. We don't really use the phrase cage framing anymore, so I'm using that for the archaic structural type. I want to give you examples of these different types to try to get you through what people were doing. Look, it's a skyscraper. Doesn't really seem like one, right? And I'm going to come back to why it doesn't seem like one. This is the Spanish Flats, as it was typically known, because the building was built in 8 segments, each of which was named after a city in Spain. The official name of it was the Central Park Apartments. The trees on the left are the south end of Central Park. Nice place to put a big apartment house facing the park. The floor plan on the right is actually, let me see if this, the floor plan on the right is this segment right here. You can see that bay window, you can see the entrance, there's the entrance. Anyway, it's a 9-bedroom apartment with 1 bath. So it would have been functionally obsolete had it not been demolished long ago. But if you look at the floor plan, you see that some of the walls are very heavy and some of them are light. The heavy ones are brick bearing walls that met the requirements of the New York City Building Code for thickness based on height. The light walls are terracotta partitions. This is 1883, which means it was built under the first modern building code in New York, which is 1882. There were building codes prior to that, but they were at best partial in terms of structure. So here you have it. This is what a very big bearing wall building looks like when it's not a church, when it's a commercial building, a building built to rent out apartments. I have colleagues who think they can tell if a building has bearing walls or not by looking at it. And I show them the picture on the left, which is the Healy building in New York, 1891. That's a bearing wall building. That has a great deal of window area for a bearing wall building. The old New York City building codes were based on a certain amount of wall for the height. And what they said was that you were allowed to have as much window as you want, but the cross-sectional area of the wall couldn't be reduced. So if you have very big windows, like you see right there, the piers between the windows get very thick, out of plane. This was an office building in an area without many office buildings, actually in the area where there were tanneries. Not a high rent area, and therefore not worth, 1891, people were already building skeleton frame buildings in New York, but no one was going to spend the money to build a skeleton frame building in this area because it simply wasn't worth it. The building on the right is the same year of construction. It's the Stokes building. This is an office building that was built not far from Wall Street. And this is a fairly ordinary 1890s office building for New York. Now, both of these buildings had exterior bearing walls, interior cast iron columns, either wrought iron or steel. They've both been demolished. There's no way to find out. Floor beams and terracotta tile arch floors. I'm going to come back to the floors in a little bit. But you know, the idea that a bearing wall building has very dense masonry walls and a skeleton frame building has lighter walls isn't necessarily true. Here's one of those unicorns, a cage frame building. This is the Mechanics Bank building in Brooklyn, downtown Brooklyn. Built, I think, in 1898 or something like that. This is the photograph that I'm working with on the left. I've blown it up, and I'm going to show you this in a plan in another building shortly. You notice there's not really a spandrel beam here. It looks very wrong to those of us who've worked on skeleton frame buildings. They're putting up columns, and each column supports a girder. What there is this very small beam that supports, here's the tile arch floor, and there's it's a channel to support the last panel of floor. But they don't need a spandrel beam because what's the purpose of a spandrel beam if it's not supporting the wall and there's no lateral load system? The lateral load system in this building is the masonry walls. So what they've done here is they've only included metal framing where they need it. And the other thing that you will note, if you look at the picture on the left, the frame is pretty much complete. They're still installing the floor up here. But what is happening is that they are building the exterior wall as you would expect in a bearing wall building from the ground up, because they have no choice. It is a self-bearing wall. These are different versions of technological ideas. They're all based on the same technology. Every building I've shown you so far, the bulk of the wall is common brick. They have different veneers on the outside. Any columns are cast iron columns. The beams are wrought iron or steel, basically identical I-beams. And the floors are terracotta tile arch. The technology used in all the cases is pretty much exactly the same. Back to the world building again. So I'm going to show you 3 buildings in a row designed by the same architect who probably is not familiar you're not familiar with, George Brown Post. If he had been in Chicago, you would know him better. He was arguably the foremost architect in New York in the 1890s, president of the American Institute of Architects for a time, had an incredibly successful practice. And interestingly enough, his education was as a structural engineer. I don't think he designed all of the structure for his buildings because he was running a large firm. I don't think he designed all the architecture for his buildings either. That's what partners in large firms do, is they delegate. But he certainly knew the issues and was involved with them. So I want to look at 3 buildings of his over the space of, I think it's 7 years, where you can see his personal evolution. So the building on the left was the headquarters for the World newspaper, the New York World newspaper. You see that row of windows right below the dome? That was Joseph Pulitzer's office. It's sort of one of history's ironies that Pulitzer's name is these days known for quality in journalism, given that the World newspaper was a rag. Yellow journalism, horrible things being printed, such is life. On the right, we have a series of sections through the walls of the building. This is only the bottom half of the building. If you look at the section at the rear wall, this one right here, for example, you see the way the wall keeps stepping out as you go down? That's the New York City Building Code text turned into a building. In other words, the code required walls to get thicker at a certain amount based on height and based on the structure of the building. And there it is, in the rear, on the lot line wall where there's no ornamentation, that's exactly what happens. The blue color is stone. So the 3 sections on the left are showing you the ornate street facades where there's a great deal of stone ornament. They don't get thinner quite the same way, although you can see a little bit of taper. But what I want to bring you see that stone right there? That's the base of a cast iron column. And you can just, you can just barely make out the column going up on the inside face of the wall. That's what a cage frame building looks like in a wall section. You've got a cast iron column which is carrying the interior floor load of the building, and it is built into a large brick wall. Again, tallest building in the world for 2 years, and demolished for a highway ramp, so much for fame. The point I really want to make about this building, from our perspective today, it's not a good structure. Post was one of the foremost architects in the country at the time. This was a wealthy client. He could do whatever he wanted. The client wanted a showy building. This is a very prominent location. That is the foot, that thing that looks like a shed on the left is the foot of the Brooklyn Bridge. That is the train station for the trains that came over the bridge. It's facing City Hall Park. This is as public a location as you could possibly have. Pulitzer wanted a showcase building. Why did Post use this structure? And the answer is he was using structure in his mind in the most efficient way possible. He was using cast iron, which is strong in compression, for columns. He was using wrought iron, good in bending, for beams. He was using brick for the exterior walls because that's what you use for exterior walls, except where you cover it up with stone to make the building look more expensive. In 1889, when the building was in construction, the worst failures of cast iron in the US certainly were still in the future. So he was logically using different materials in a way to combine them as a hybrid structure to achieve the goal he wanted. It's something that we still do today. There are people build very tall buildings using hybrid structure, concrete cores and steel framing around them, for example. So what you want to avoid when looking at something like this is what historians call presentism. You don't want to interpret what he was doing by the standards of what we do today, because if you do, you'll say, well, he was wrong. He wasn't wrong. He was actually being meticulously logical in a way that was just about 1889, 1890, he was just about to be proven wrong, but you don't know what's just about to happen, right? You only know in retrospect. So 1890, the first the first skeleton frame buildings are constructed, and I'm going to come to them in a little bit. This is 1892. This is Post again. This is the Havemeyer building, and there's the elevated train running past for your oldie-timey feel. This is a cage frame building of a different type. I said there were two kinds of cage frame buildings. The World building relied on the masonry walls as shear walls. The Havemeyer building, which you notice is rather more slender. So it's what we would call architecturally a slab, right? Small in one direction, big in the other. Had a full wrought iron frame, and you can see the built-up columns as little winged boxes in the middle there. The frame had cross bracing. The frame had cross bracing in the form of wrought iron X's in various portions, particularly around the elevator shaft, which is off here on the side of the plan. So he wasn't relying, this is 2 years later, he's not relying on the masonry anymore for lateral load. He's providing his own lateral load framing. But look at that pier right there, that huge pier, and you can see these huge piers. Look where the column is. It's way on the inboard side of the pier. That column can't, I mean, it could support the pier, but it would be very difficult to support all that masonry from a column located at one face. So that's a tip-off. I happen to know more about this than this picture shows. That's a tip-off that this is a cage frame building. The exterior wall is self-supporting, which is, it's slenderness, structural slenderness, height divided by least plan dimension of 4.1. This is starting to become a slender building. I'm going to be referring to slenderness more as I go along. I just want to give you a reference point. The Empire State Building, which is a notably slender skyscraper for the 20th century, has a structural slenderness of 6. The Old World Trade Center and the New World Trade Center, for that matter, it's less than 6. Sears Tower in Chicago is about 6. Until 2000 or so, it was relatively rare you would get a very tall building with a slenderness of greater than 8 or so. So a slenderness of 4 for 1892 is pretty good. Post again. This is the St. Paul building. It's really one of his worst architectural efforts. The picture on the left is sort of the best view of it. And yeah, exactly. That's the best view. This is the very short facade is Broadway. The diagonal facade is Park Row. The side facade is Ann Street. That's it from the back. And isn't that elegant? Right next to it, we have the Park Row building from the back, and also another building that looks much better head-on than from the side. Park Row is still there. St. Paul was demolished some time ago. I should also mention in passing, I have a personal connection to a lot of these buildings. My father's first job after he got out of the Army in 1952 was in the St. Paul building. 1897, and it has a skeleton frame building with some very interesting details. Post wrote an editorial, I'm trying to remember now, he wrote it, I think, for the Engineering Record, and it was reprinted in newspapers, including the New York Times, saying, I'm concerned about people using steel framing inside the exterior walls because it's going to rust. He was not wrong, and a non-negligible portion of my practice is fixing the steel on these old buildings. But at the time, it was something of a minority position. That's the wall section of the building, and you notice that the column is entirely inboard of the exterior wall. He doesn't trust the waterproofing. He's putting his columns where they're safe. And then he has, you can see it, this is a plan, he has a double girder that cantilevers past the column to hold up a little spandrel beam, and that's how the exterior wall is supported. So he's gone to enormous lengths to not have the important structural steel of the building inside the wall, but it is a skeleton frame building. He also provided this detail at every other floor rather than at every floor. So he was really looking to minimize the amount of steel that might start rusting. One last comment about that photograph. And the caption of it is from 1901 and was correct in 1901. Those are the 2 tallest buildings in the world, using the definition of building I've been using, where you have occupied space. Park Row on the right, St. Paul on the left, 2 tallest buildings in the world in 1901. And in case you're wondering why the St. Paul building is called the St. Paul building, there is St. Paul's Chapel right there. The other thing is this photograph, given the angle, is probably taken from the Healy building, that bearing wall building with the huge windows. See all these little industrial buildings here? Remember I said the Healy building wasn't in such a great neighborhood? Let's start with the photograph. The tall thing is the Singer Building's tower under construction. The thing with the white brick facade that's in construction is not the Singer Building, it's the City Investing Building. The 2 buildings were literally side by side and actually at the ground floor in contact with one another. It is impossible to get a picture of the Singer Building that doesn't have the City Investing Building messing it up. The City Investing Building, and it actually looks better here than it did when it was completed. It was a hideous, hideous building. Singer Building is the weirdest looking skyscraper I know of prior to postmodernism becoming a style. But at least it was sort of elegant. It was very tall and slender. And not only were they next to each other, as you can see, they were built simultaneously. The text, and one last thing about the picture, the City Investing Building is showing you what you can do with a skeleton frame building. You can start the masonry wall in midair, which to us is nothing, right? That's the whole point of supporting the exterior wall on the frame. As late as this photograph in 1906, 1907, people on the street, people who write newspaper editorials, people who write architectural magazine articles but don't know much about engineering, were still marveling at that point that you could begin a masonry wall in midair. This was the future. This was something beyond conception. And that leads me to the text on the left, which is from 1896, an editorial in the Engineering News, You all know how to read, but I want to editorialize about it a little bit. The construction of exceptionally high buildings with steel framework, which now forms such a noticeable feature of larger American cities. In 1896, there were maybe 30 steel skeleton frame buildings in the US, almost all of which were in New York and Chicago. So they're beginning with some hyperbole. Has led not only to the development of a new and large market for structural steel, that it did, but also to new problems in structural design. These difficulties are probably appreciated not at all by the owner. Everybody here in private practice is nodding at this point. And only to a limited extent by the architect, unless he is himself an engineer experienced in structural work, such as George Post. And the design engineer can expect but little credit for the successful results of his labor, since the work is all built in and enclosed as soon as erected. In other words, the picture on the right happens to capture that moment, but once the building's complete, you don't see it anymore. The casual observer never gives it a thought, and even if anyone were interested in it, it is hidden from examination. The first time I read this, which is now 25 years ago, I immediately named it The Engineer's Lament. It's still true today, and it does describe part of the problem in researching these buildings. You can find architectural descriptions without much difficulty. You can find floor plans. Finding information about the structure can actually be surprisingly difficult. Let's say you disagree with what I said earlier, and you insist on skeleton frame buildings, skeleton framing as being the criteria for a building being a skyscraper. Well, then you have a tie. The building on the left is the Manhattan Building in Chicago, and I have never stopped laughing at that name given the issue in hand. The building, and it still exists, it's been converted to apartments. The building on the right, with a slenderness of, I think it's 6 or so, is the London and Lancashire Bank in New York on Wall Street. The temple next door is a government building. Let me get the dates for you exactly. The Manhattan Building began construction in June of 1889 and was finished in June of 1891. The London and Lancashire Bank began construction in October of 1889, which is to say 5 months later, and was finished in May of 1890. It's a much smaller building, right? So it was finished over a year earlier. The two buildings were built simultaneously. Neither one of them influenced the other, and they are the two first steel skeleton frames, as far as I know, anywhere. So it's a tie, Chicago and New York tied. If you insist on skeleton framing, which as you know, I don't. But the problem with what I've just presented you, I've just given it to you in roughly chronological order and in engineering logic order. Bearing wall with walls at the interior, bearing wall with columns at the interior, a cage frame where the walls provide lateral load, lateral resistance, a cage frame where the walls do not provide lateral resistance, but the frame does, and then skeleton framing, right? That's a nice logical sequence. But that's not the way things work. In reality, I've cherry-picked the examples out of literally hundreds of possible buildings that I could talk about. This is actually one of the things that got me interested in doing this research, was that if you look at architectural histories, they keep talking about the same 24 buildings. And I thought, that can't possibly be what happened. There were so many other buildings built, it can't be that those two were it. So this is from 1891, a fellow named William Fryer. Fryer is an interesting guy. He basically wrote the structural portions of the 1892 New York City Building Code, which was the first one to really acknowledge that metal framing mattered. He was a structural engineer. He did dabble in architecture. And he went on, after he wrote the code, he went on to private practice completely. And this is from an article he wrote illustrating, as he saw it, the evolution of the skeleton frame. On the left, you have, the three things on the left are plans. On the left, you have a cast iron column at the interior of the building. And then to save a little bit of room, you got to maximize rentable floor space, you push the column into the pier. And then the engineers say, well, why isn't the column in the middle of the pier? So you put the column in the middle of the pier. And on the right, you have an isometric showing you what that would look like. And this, the detail on the right is a very common one in buildings built in the 1880s and 90s in New York. Now, he's showing cast iron columns. I would say that he's got a problem for lateral load if he thinks that's a skeleton frame building. which brings me to how accurate was what Fryer was saying. The tall building in the center is the office building of the Jackson Iron Works. Jackson Iron Works built a lot of the early, or built the metal framing for a lot of the early skyscrapers in New York. This is not where they did their metal work. That was in cheaper land. And on the right, we have a floor plan. And if you look closely at this floor plan, that is exactly the detail that Fryer drew up. And there it is, cast iron columns set into the wall. Now, there's a couple of interesting things about this. The first one is that the building has a slenderness of over 6. And the second one is it has no lateral load system. These are cast iron columns. You can't make a moment frame the short direction. Look at the front facade. It is very much open with that huge arch down at the base. There's no way that that's a shear wall. And even if it were, how are you getting the load to that shear wall? This building, like quite a few 19th century buildings, did not have a functional lateral load system, which if you ever have doubts about, the second or third place behind the decimal point in your calculations, take a look at something like this. And, it stood till the 1960s when it wasn't actually completely demolished. It was turned into a 2-story building. The building on the right is still standing, as is the building on the left. But this building has this huge flank picking up wind load, and New York gets hurricanes with no lateral load system. So one of the points I'm trying to make here, this is 1891. This is after the steel skeleton frames had already been built. Evolution doesn't move in a straight line. Two very famous buildings that pretty much kicked off the entire Chicago versus New York nonsense. The one on the left is the home insurance building, which I'm going to guess some of you have heard of, may very well have heard of it as the first skyscraper, particularly if you trust Wikipedia. That's 1885. Building on the right is the Tower building in New York. You can't see it from this photograph. It had the same basic geometry as Jackson Iron Works. It's a slab. The home insurance building, and I copied into my notes here the entire description from an engineering study that was made when it was demolished. By the time it was demolished in 1932, it had already become famous as, quote, the first skyscraper, unquote. It was not the tallest building in the country in 1885. It did not have a steel frame. The columns were cast iron. The frame did not resist lateral load. The exterior wall did. What it is the first of is it's the first building where the frame did not contribute, where the exterior wall did not contribute to supporting the floors. In other words, it's the first cage frame building, which is not nothing. It is a moment in technological evolution of tall buildings, but that's not what people think. What people think is it had a steel skeleton frame. It was the tallest building at the time. It wasn't even in the top 10. So it's an interesting building. It's the first cage frame building. But I keep talking about evolution. So it's the first building where 100% of the floor load is carried on the frame, not on the exterior walls. What came before it? Well, this is 1885. In 1884, the produce exchange in New York was completed. And the produce exchange had a metal frame that carried the floors, but the last panel of floor, the last vault of terracotta rested on the wall. It's about 5% of the building weight. So if this is 100% of the floor load being carried on the frame, the produce exchange the previous year was 95% or so. As any elementary school teacher will tell you, there's a big difference between 95% and 100%, but it's not groundbreaking, right? It's a logical extrapolation of what people were already heading towards. And if it hadn't been this building, it would have been some other building the same year or the year after. The Tower building is a grotesquerie. There's just no other way of describing it. It basically was 6 stories, a 6-story high bearing wall building sitting on top of a 7-story high cage frame building that had some diagonal bracing in it. And there's a really insane story as to how that came to be that isn't worth going into. The building didn't make sense. It didn't last that long. It was horribly uneconomic because it was so slender. But it's worth, I said that this kicked off the Chicago versus New York thing. Tower was built in 1889, 4 years after home insurance. And about 1899, 10 years later, some friends of the architect who designed the Tower building had a plaque put up on it that said it was the first skyscraper. And people in Chicago heard about this, and they said, we need something that was built before that. And what they found was the home insurance building, and they said, this is the first skyscraper, because it was built before the Tower building. And that is the origin of all of that discussion that still goes on today. And yeah. Sorry, I keep accidentally hitting that menu. This is, as of, let me think about this. This is 1910 or so. At the top, you have the skyline of Chicago as seen from Lake Michigan. At the bottom, you have the skyline of Manhattan as seen from New Jersey, looking across the Hudson. They're not at the same scale. That is the tallest building in Chicago at the time. That's Montgomery Ward building, and is, I wrote this down in metric, 92 meters tall. The tallest building in New York, there's the Singer building, and there's City Investing blocking the view of it. The Singer building is 187 meters tall, so it's about twice the height. So these are very much not at the same scale, these two photographs. My position, and has been for years, is I dare anyone to draw a line and say this building is a pre-skyscraper and this one is a post-skyscraper, because it is a continual process of evolutionary change of technology. There are a bunch of technologies in there, and what I want to do next, so people upended the entire way that they built big buildings very rapidly. Why did they do that? It was expensive, it was difficult. It, for a while, made things actually less safe. Why would people go to all this effort? And just, I want to add a minor content warning. I am going to be discussing some unpleasant things involving buildings. One other comment is I'm going to be using the word fireproof because that's what people called it back then. Today we would say fire rated. This is a very partial list of fires in the United States that destroyed a significant percentage of a city. New York, we got it out of our system early on. The Chicago fire is the one you've heard of. I want to compare the Chicago and Boston fires, which is the next slide. To give you a sense of what these fires were like, the photograph there is a panoramic photograph of central Boston. That is the middle of the downtown area of Boston, November 10th, 1872. And if that reminds you of looking at the result of aerial bombing, well, that's what you got. It is extremely hard to overstate how flammable American cities were in the 19th century. People in Europe had had experience with this kind of fire much earlier on, and as a result had changed the way they built much earlier on, which is to say before industrial materials were available. In other words, if you look at a European city in that era and you look at an American city in that era, the American cities are much more flammable. Here's the comparison. So 2 fires a year apart. Chicago, 17,000 buildings were destroyed. But most of them were wood frame houses. Most of them were actually shacks. Boston, it's 700 plus buildings in the central business district. Obviously, Chicago's much worse on the human toll and much worse on area. Look at the bottom line of that table. Chicago had 17,000 buildings destroyed, but only 3 times as much in insurance payouts. So the lesson here for insurance companies, Chicago in 1871 was a boom town. It wasn't even 40 years old yet. It was cheaply built. The buildings were meant to be temporary. The city was growing so rapidly, you knew you were going to abandon that building and build something else. Who cared? Boston, it's one of the oldest cities in the United States. Those were substantial buildings that were destroyed. So Chicago, the insurance companies paid out a lot of money. But they said, we know about this problem. Boston terrified them because if that happened in New York, every insurance company in the United States would have been bankrupt right then and there. People don't like going bankrupt. So let's go through a few examples of this. The building on the left is the Windsor Hotel, built in 1873 in New York, which is to say after the Boston fire, but before the New York City Building Code had any real kind of fireproofing provisions. The picture on the right is after an hour-long fire in 1899. And just so you understand exactly what you're seeing, you see this building in the background here past the pile of rubble. That's that row house. So the building had a brick wall at the exterior, wood interior floor framing, sticks, 3-bys, wood elevator shafts, wood dumbwaiter shafts, wood stairs. I think anybody who knows anything about modern construction would be horrified just walking in that building. It did have some fireproofing in the form of plaster finishes, but when you have a wood elevator shaft, it really doesn't matter if you have plaster finishes. The pile of rubble on the right here had been the Keep building. The building across the street, which as you can see had some significant damage, is the Manhattan Bank. Manhattan Bank was repaired. The photograph on the right is a photograph that was taken when it was designated as a landmark building about 20 years ago. What happened there is much more interesting. The Manhattan Bank building was sold to the public and to its owners as a fireproof building. However, it was fireproof by the standards, let me just get this, when was it built? Early 1880s. It was fireproof by the standards of the early 1880s, which is to say things like the bottom flange of the girders were exposed. The floor was non-flammable, it was terracotta tile, but the wrought iron was exposed to the heat of a fire. When the Keep building caught fire, the heat of that fire caused the collapse across the street, which gives you a sense of how intense the fire in these old wood frame buildings, well, wood frame interior buildings were, that the heat could leap across a 50-foot wide street to destroy a building like that. This little building right here is the Rogers Peet store, which was a men's clothing store. Mid-19th century building, wood joist floors, brick walls. Next door you have a modern fireproof building. Drawing a blank here. The Home Life, that's New York's Home Life building as opposed to Chicago's Home Life building. And as you can see on the right, when Rogers Peet burned down, it started secondary fires in Home Life. What's interesting here is that that building is still there today. It was repaired. There was very little structural damage. The terracotta tile fireproofing worked. This is an 1890s building. Let me give you a more recent example. I took the photograph on the left in November of 2001. That is 90 West Street, otherwise known as the West Street building. That building was on fire for 2 days after 9/11. Not a huge fire, but when we walked in 2 days after the event, there were still smoldering piles of former contents in there. There was almost no structural damage. The building survived an uncontrolled fire with almost no structural damage because of the terracotta fireproofing. So this is late 1890s. People had figured out how to make buildings fireproof. They had addressed the problem that the 1870s had caused. They hadn't addressed every problem. This is the Darlington Apartments. It was under construction when it collapsed. It was up to the 11th of what were planned to be 13 stories. If you look closely at that floor plan, every single column in the building was loaded eccentrically, and they were cast iron. All it took was one problem, and the problem in this case appears to have been that a plasterer put all of his bags of gypsum in one spot. The building came down in the space of 30 seconds or so. A similar building, but much stockier. The Parker building had this was a loft building, a manufacturing loft building, had a fire. And as you can see, the hatched area is what collapsed. You can see the sky through the facade on the picture on the left. This one actually was written up in the UK. I'm not sure why. There was an insurance report, which I've never been able to track down, but I was able to track down the UK commentary on that insurance report. That's what happens to cast iron columns when you heat them enough and then let them collapse. But what's interesting is that even here, they identified what the problem was. The columns were all covered with terracotta fireproofing, and then the electrician cut into the fireproofing to run wire. Oops. And finally, a very famous fire from 1911. The Triangle Shirtwaist Company occupied the top 3 floors of the Ash building. 140 people died in the space of 15 minutes in this fire. The building was barely touched. The building is intact. After the fire, the factory reopened less than a year later. So what this was a turning point because it proved that A, no fire was going to bring down one of these modern buildings, and B, you need egress. It's not the structural fireproofing that's going to save people, because it did not at Triangle. A few trends worth comparing. Most of the lines go up. The US was growing tremendously between 1870 and 1900. 3 lines don't really go up. Construction cost sort of peaks in 1890. Brick production is declining. And new building permits, if you look at the beginning and the end, is about the same. Buildings are getting bigger. That's why the number of building permits doesn't increase. That line zooming upwards, the blue line, structural iron and steel is taking over from brick. On the left, a chunk of lower Manhattan, actually very close to my office. On the right, one full block of Chicago's Loop, except this map actually is from before it was called the Loop, because it wasn't called the Loop until they built the elevated railroad going in the Loop. The pink buildings are not fireproof, the tan buildings are fireproof. But what I really want to draw your attention to is Chicago, you have a relatively small number of buildings on relatively big lots. In New York, you have really horribly fragmented land ownership. And this is, again, comparing a relatively young city. Chicago these are both 1905 or so. Chicago in 1905 is 70 years old. New York in 1905 is, whatever it is, close to 300, 280 years. A lot of time for people to sell pieces of land to one another. And why does that matter? Because you get things like this in New York. That's the Manus building on the right. That is not one end of the Manus building. That is the Manus building, the thing with the cornice. And let me give you the exact dimensions because I have a hard time believing them. Okay, I'm going to give it to you in imperial. I'm sorry. 16 feet by 55 feet, 11 stories tall. I've worked on row houses that have a footprint twice the size of that. This is what happens when you don't have zoning and everybody says, I'm just going to max out the value of my lot by building up with a steel frame building. The chart here, and I'm running short on time, so I'm not going to spend too much time on it. The blue dots are New York, the red dots are Chicago, and this is structural slenderness going up the side and base width going across the bottom. And if you look at this chart closely, let me get the exact thing here. New York has almost all of the buildings under 10 meters wide. New York has every single building with a slenderness of 6 or greater. And actually, see that one dot that's all the way on the left? That's the Manus building. Most narrow building built high enough to call it a skyscraper. What does this mean? Well, it means that people in New York were experimenting on sort of the cutting edge of what they could do. They were building slender and more slender buildings, and I think as structural engineers, I hope you'll agree with me that slenderness is more difficult than height. If you give me a stocky enough building, I'll build 3 miles high, I don't care. But if you tell me that I have to have a structural slenderness of 20, that's going to be difficult no matter what height it is. So this is what's driving this sort of frantic search for new technology is slenderness, which is the result of land fragmentation, which is the result of social issues rather than engineering issues. I have one last thing I'm going to say. I've run a little bit over. And that is, there are implications for this in where we are today. First of all, there are implications in where we are today because since 2000, people have started building buildings in New York with slendernesses of over 20. If you look up Billionaire's Row, which is a series of very tall, slender apartment houses along the south end of Central Park, those are tremendously tall buildings, and they are all very, very slender. The second one is that when you have technological evolution, you have dead ends that maybe aren't dead ends forever. The obvious example is, do cage frame buildings make sense today? And think about it. If you could have a continuous exterior wall with your structure inboard of it, that sort of makes sense for things like insulation, for longevity, for, as George Post wanted, protecting your structure from the weather. It's not so easy to do if you're in an area with high seismic loading, which we are not in the UK, right? And in portions of the US, you're not. But it is, I think, an example of a currently dead technology that perhaps should be brought back to life. Thank you very much for your attention.